Morning, everyone. This is Shauna, and I'm here in this video to show you three integrals that involve tangent that might give you some problems on the homework. So without further ado at this time, let me share screen and I'll show you the first one on the whiteboard. The first one is tangent x times secant cube x dx. This one is the most straightforward. Integrating tangent doesn't have like a particular approach all the time, like sine and cosine do, whether the power is even or odd, isolate a sign. And that's what I hope to show you in these three problems. We know that the derivative of tangent is secant squared, but if we let u be the tangent, we'd only have two of the secants and we'd have a secant left over. So that wouldn't be very useful to us. You might think of changing the secant squared to part of the identity with the tangent also. And then you'd have a power of the tangent, which would actually be probably just as hard to integrate. What I did was I said, well, I know the derivative of secant is secant x tangent x. So if I let u be the secant, then something interesting happens. If I let u be just the secant to the first power, then I know that u squared is secant squared x. And the derivative becomes secant x tangent x. Now, at first you're thinking maybe that doesn't quite work, but if you notice here, you have tangent x times secant cubed. So if you rewrite this so you can see it as tangent x times secant squared, then you can see from here that the integral falls into place. If I have tangent x times secant tangent x times secant squared x times another secant x, this just becomes u squared, that's my secant squared. And then I have tangent secant dx, which is du. So this essentially is the integral of u squared du, where u is the secant. And then I have, well, of course, 1/3 u cubed plus a constant. Don't forget my integration constant. And so therefore, this problem resolves into 1/3 secant cube x plus a constant. Okay, that's the first one. Now, the other two are more difficult and require more manipulation of this du. You'll see that in just a moment. Let me share this screen with you and pull it over. Okay. I'm going to make sure that I'm sharing the right screen before I record. Okay. Now, this problem is a power of tangent, tangent to the fifth x dx. And so I started by writing it as tangent to the fourth x times tangent x dx. I should have put the dx after, but I was thinking about tangent to the fourth. Anyway, the one of the Pythagorean identities, which is the one that you see here, 1 plus tangent squared x equals secant squared x, it's hard for me to remember. So I always derive it, and the way you derive it is with the famous Pythagorean identity that it may be one of the few identities that you actually have memorized. If you have not, I would definitely put it on my memorize as soon as possible because it's extremely useful and you can derive other identities with it. Anyway, if you divide the Pythagorean identity cosine squared x plus sine squared x equals 1, if you divide the whole identity by cosine squared, you get 1 plus tangent squared is secant squared x. And that proves very useful to us here. Obviously, we need tangent squared. So I'm going to manipulate that to get tangent squared x is equal to secant squared x minus 1. Then I can write this integrand as secant squared x minus 1 quantity squared times the tangent of x. And I have a similar problem to what I had in the other one we just did, where I have the u is the secant of x. So this is u squared minus 1 quantity squared. But my du is a little bit messy this time. So my du here is going to be secant x, tangent x, dx. But I don't have this secant x here. And I can't just throw it in or make it go away. What I can do is, I know I can substitute for this first part of the integrand. What I can do is manipulate this expression and isolate tangent x dx and see what happens. If I do that, essentially I divide by secant squared. So I get du over secant squared x is equal to tangent x, but u is the secant. So I have du over u, okay? And I can write this piece as tangent. So now I can say that this integrand, the integrand of secant squared x minus 1 squared times tangent x is u squared minus 1 times 1 over u du. I just wrote this as 1 over u. I brought the 1 back out. And then you're thinking, okay, but what do we do from there? Well, what I do from there is I go ahead and expand this polynomial, this second power. So I get u to the fourth. Remember, I have to FOIL. So I get double the middle term minus 2u squared plus 1 all over u du. Now, treat this as 3 separate fractions. You can divide every term by u because there's only a single term down here. So u to the fourth divided by u is u to the third. 2u squared divided by u is 2u, and 1 over u du. Okay, then integrate each term. So you get, remember, we add 1 to the power and divide by the new coefficient. So we get, the new power. So u to the fourth over 4. This is minus 2u squared over 2, and the 2's will cancel, plus the natural log of u, absolute value of u plus a constant. So here I canceled the 2's in the middle term and I substituted. And we end up with 1/4 secant to the fourth x minus secant squared x plus the natural log of the absolute value of secant x plus a constant. Okay, so that's another approach by using identities. I'm going to show you one more problem that involves a tangent. So let me show you this one. This one is the integral of 1 minus tangent squared x over secant squared x. And I said, be careful. because it's very tempting if you're like me to say, wait, is that secant squared x minus 1? What is that? I know that's something with secant squared in it. So I put it over here for you. Tangent squared x plus 1 is secant squared. Now I could have plugged that into this equation, and then I would have had conjugates at the top and the bottom, but I wasn't too keen on that. So I decided to take a different approach, and I decided to divide both terms. This is one term at the bottom, secant squared x. I decided to divide both terms by secant squared. So this is 1 over secant squared x dx minus tangent squared x over secant squared x dx. Do your little manipulations algebraically. Secant squared is 1 over cosine squared. Tangent is sine squared over cosine squared, and secant is 1 over cosine squared. So this actually becomes a very nice little integral. You get the integral of cosine squared x minus the integral of sine squared x. And you're thinking, okay, but that's going to be a mess to integrate that. You could use an identity to rewrite cosine squared. What I did was because I had cosine squared minus sine squared, I put this back together, and I recognized that this integrand together is a different identity. It's cosine 2x. And so my integral became very elementary after that, because I can make u the argument of the trig function. Du is 2 dx, and then use a fraction to help me. So what I end up with is du is 2 dx, 1/2 du is dx, and what I get is the integral of 1/2 cosine u du. And remember, the derivative of sine is cosine. So the integrals don't switch signs, the derivatives do. But the derivative of sine is cosine. So this is 1/2 the sine of u plus a constant. U was 2x. So you get 1/2 the sine of 2x plus a constant. I hope that these 3 examples of integrating with tangents have helped you a little bit. And I look forward to seeing you in my next video. Thank you, everyone.